Thanks, everybody. Good afternoon. Theodore Alvarez. I'm honored here. We today share is the theme is the factory influence in many core processors. Thank you for your attention.
So my name is Sam Falvo. I'm just been working on my Kestrel 3 project. Recently have the success of getting the CPU to actually run software in Verilog simulation. So I'm pretty pleased about that, and I've said, cool, I'll do a poster session about that. The Kestrel 3 project in general is much more than just the CPU, of course. It's a fully open source computer. I'm of course starting very slow and very small and eventually going to work up to a regular desktop class machine. At least that's my ambition. As with Eric's talk earlier today, the purpose, the whole point is no binary blobs. I want everything to be fully documented. How many people here remember the Commodore 64 or Commodore PET? You remember you could get one book that has everything you ever needed to program that machine, and that's my goal for the Kestrel 3, is to be able to have one programmer's reference manual. So that's the goal for that. If you're interested in talking more about this, I'll be at the poster session, obviously. And with that, I will pass the mic on to the next person. Thank you.
My name's Mark Gotcho, and I'm a PhD candidate at UCLA. So I'll be presenting a poster on software-defined error correcting codes. And I'll briefly give you a quick motivation. You can come talk about it. So essentially, errors in memory are causing lots of system-level crashes when they're detected and uncorrectable. So with some collaboration at UCLA with some of these coding theory people, we architects, we came up with some new way of essentially pushing beyond the error correction boundary currently by allowing us to recover from these detected uncorrectable errors. So we do that essentially using side information about data instructions in memory, and that's why I'm here at the RISC-V workshop, because we're specifically targeting RISC-V for our early work on this. So the essential idea is that when you get this detected uncorrectable error, instead of doing something really bad, it turns out that you can compute from a small list of candidates what the actual original data was, and with a reasonable degree of confidence, recover the original information. So instead of crashing or poisoning your data or doing something like that, we want to essentially heuristically recover. So if you're interested in hearing more about it, come see my poster. Thank you.
Hey guys, I'm Austin Harris from the University of Texas. I'll be presenting an approach called WASP that tries to defend against these utilization-based side channels, such as the memory bandwidth that was mentioned during the Sanctum talk. So our solution is to, at runtime, we shape the utilization that the victim has on the resource, and we ensure that it is statistically indistinguishable across the different inputs that the program might be running. And we're able to do this by optimally minimizing the slowdown within a user-provided privacy parameter. And we do a prototype of this in the Rocket core by having a SHA accelerator with multiple cores sharing it, sending commands through our queue that shapes the traffic. Thanks.
Hello, I'm Shunpei Kawasaki from SHC, and I'd like to present this embedded core that with a 64-bit MCU, and this is like a kind of unusual choice for like the MCU, but at 40 nanometer process, it is pretty powerful and very low cost too. So this is my take of how we can shape that 64-bit MCU with RISC-V 64-bit architecture. So when you have time, please come to my presentation. Thanks.
Hi, everyone. My name is Ben Keller. I'm a PhD candidate at Berkeley, and I will have a demo this evening of our latest RISC-V silicon. I'll be talking in much more detail about the system tomorrow afternoon in a full talk, but to give a whirlwind tour, we've integrated a RISC-V rocket processor with a vector accelerator that's being supplied by integrated DC-DC converters and an adaptive clock generator. The SoC also includes a second smaller core specifically for power management, such that we can actually run arbitrary C code to actuate voltage changes and measure, in response to measured program counters or counters in the system, while booting Linux or doing other interesting things on the main application core. So I guess having demos of functional RISC-V silicon has lost some of the novelty that it had a couple of years ago when we started doing these. But nonetheless, if you want to talk power management or see Linux running on our system, please stop by tonight. Thanks.
I'm Kurt Keble at MIT. I'll be discussing some of the meeting notes for the RV128 discussion group. So feel free to come by and grouse if there's anything you'd like to see in a 128-bit extension. We can talk about it. I already have some insights now after seeing Steve's presentation earlier. If you've read the IEEE Spectrum piece by Bunny Huang, there's some market dynamics now that are putting us in what Kurzweil calls an inflection point, where some of the technology disablers are gone now from us doing a boutique run of 1,000 chips for 1,000 people in the world that we know need a 128-bit processor of some variety. So we'll pursue some of those issues, find a candidate RV64GC architecture to piggyback on, look at a proposal, move it through committee, probably do a poster at the Boston area architecture conference, which has a surprising number of RISC-V posters, and see if we can't, expedite this process. There's a lot on the table, but there's a lot of opportunity to talk about it. So come by our poster and see if you can give us some ideas.
My name is Michael Korpi. I'm here to present an open source project I'm working on. UNNI, it's called. It started all with that I tried to convert from a Cortex-M0 system to RISC, but I got some hang-ups, I have to say. And these 4 points I have here is basically why I started this open source project. So I wanted a very easy migration. And most systems were Harvard systems. And I wanted one non-mine because of the Cortex-M0. And I wanted a very small core. So that drew away a lot of the cores available, I have to say. It also need to be ASIC implementation, so asynchronous reset and so on. And I've seen the chisel, and that is really great. But from where I come, it will be very heavy to get in. Especially, I have a lot of projects going to automotive, and it will take years to convince them to switch to something like this. And lastly, important for me is interrupt latency and context switching. And many of the cores I looked at lack in this. So that's why I'm starting this project. And please come by, give me some feedback. The poster is more a starter for conversation than actually the system. Thanks.
Hi, I'm Tim Newsom with Sci-5. I think I've been up here at every workshop this year saying something about debug. Obviously, it works in Silicon. I guess the latest trick is that it downloads directly to Flash, like straight from GDB, which is kind of fun. But really, I have a demo so that you can come talk to me about debug. I want to hear what people want out of debug. If you have the chance, you're a foundation member, please show up to the meeting on Thursday at 11. And if not, in the bottom right of the slide, there's a link to the debug mailing list where you can read up on what we're doing and provide your own input. That's what I got. Thanks.
Hello, my name is Alexander Redkin, actually, and I'm executive director at the company, which name is Syntacor. We are IP company. actually located in Russia, in St. Petersburg, talking about adversaries. And we develop and license programmable cores based on RISC-V instruction set. And we also provide service to specialize those to the customer needs. So I'll have a small talk tomorrow where I will provide details about our initial line of the course, which is available for evaluation. And tonight at the poster session, we will have some demos. This will be actually SDKs, both silicon and FPGA based. And for additional details, please come and stop by. We'll provide some numbers about performance and cost of the implementation in terms of footprint, of course. And additional details will be available tomorrow. Thank you.
Hi, I'm Drew Tausig from Synopsys, and this is going to be a follow-on to the talk that Steve Cox did earlier today, the presentation on our tool ASIP Designer that's used for designing, creating your own custom processors and extending them, starting with the RISC-V model as one of our example processors, and being able to show that as a demo to answer any questions that you might have or follow on from what we did today. So if you're interested, stop by later. Thank you.
Hi, my name is Dan Zimmerman, and I work for a company called Galois, which specializes in high assurance software solutions for various applications. And we are working with bluespec on a project that we just started the last couple months called SHAVE, Software Hardware Assurance Verified End-to-End. And the idea is we want to make it possible to create practical end-to-end assurance cases for mission-critical systems that run on COTS hardware. That is, I can formally verify something about my software, and that verification relies on something that I've formally verified about my firmware, and that verification relies on something that I've formally verified about my hardware, and that goes all the way down to the silicon. So what we're doing, and this is funded by DARPA, is a small case study where we're going to do a bit of a crypto extension to RISC-V, something in the spirit of the Intel AES new instructions. Then we're going to build a thin firmware layer on top of that and a little application on top, and we're going to create an end-to-end assurance case for it. So the poster basically is going to show more about how we're going to go about doing this. We don't have a lot of concrete results yet because we just started, but we wanted to be here to introduce ourselves and let the RISC-V community know that we're working on this stuff. So I hope to see you there.
Hello, my name is John Eaton. I'm a retired ASIC designer from Hewlett-Packard. I'm here to talk about a new open source tool project called the LibreChain EDA. And the goal of this project is to create and develop and distribute these scripts that you actually run on your machine to build and do IC design. A lot of groups out there you see, they have make files calling Perl, Tickle, or Python scripts, who then call some EDA tools, who then call sed a few times to fix your output files. And when all that's working, you then hack the thing so it does recursively. And nobody wants to share their scripts because nobody wants to get all the support calls and how to make them work. But if you do this in an open source project and work with us and develop them, you can start off with working code at the beginning. You get a lot more help in people testing your code and actually supplying code that you can use for your own work. So talk to me and let me tell you what I can help you with on your tool projects. Thank you.
So hi, my name is Florian. You have seen me in the morning, and as I said in the morning, I have this ASIC demo running, or if you want to have a chat with me, just stop by, or if you have the urge to touch some circuits, hardware, just stop by. Thanks.
So Jack claims to have sent a poster preview, but it's not here. If you want to see the chip the Hi-Fi 1 board running. There's an Arduino race. There's a Hi-Fi 1 board, Arduino 101, Arduino 0. There's a race. You can see how fast chips are running. If you want to see the FPGA dev kits, the RD Freedom Everywhere dev kit, the Freedom Unleashed VC707 dev kit running Doom, you can come play Doom. Thanks.